Our next speaker is Maelie Mondelin. Is that correct? Excellent. Talking about environmental effects on galaxy evolution using CFHT and Euclid synergies. Over to you.
Thank you. So thank you, everyone. Good afternoon. I'm Maelie Mondelin. I'm a second-year PhD student at CFHT, working with Jean-Charles Cunion and Sandrine Codis. Today, I propose to discuss a bit the environmental effects on galaxy evolution using the synergy between CFHT and Euclid. So it's a bit in the continuity of some talks about the cosmic web. So keep in mind some other context. So first of all, just a bit of the state of the art. So in the standard picture, galaxies are born in small overdensities in the dark matter field, a bit around the filament, and then they evolved from filaments towards nodes, so the clusters. And during these trials, they can interact, they can be merged, and they're reshaping their morphological aspects. So the diversity of morphology that we observe today is directly linked to the evolutionary stage of the galaxy. So a question that we have today is to disentangle the question about the internal process and the outer process due to the local interaction and due to the cosmic web. So this is the first question that we have. And these questions are important for galaxy evolution, but also for cosmology, because we know that the cosmic web can influence the orientation of galaxies in the cosmic web. And this phenomena is a contaminant for weak lensing and for cosmological measurements. So that's why we need to measure this alignment on not only on simulation, but on observation. So we need to have this wide field high resolution images of a large number of galaxies. And I propose to use the LSB, low surface brightness processing on these images in order to extract the region which can be interact around galaxies. So for that, I'm using images of a local supercluster, observing at CFHT using megacam in the airband. And I have also a cluster of the superstructure observed by Euclid in the context of the early release observation, so which is Perseus. And for both, as explained before, I'm using the LSB treatment in order to have access to the outer part of galaxies which are more susceptible to interact with the surrounding environment. So the supercluster is the Pisces-Perseus, which is one of the first discovered large-scale structure on the sky. It's observable in the autumn fold and represents something like 60 degrees on the sky, so which is a really huge superstructure and really close to us at a redshift 0.017. And I have access to two regions, which is a part of the Cepheid unions for the main filament region, and also additional observation of this region with a lot of clusters. So I call this region cluster region. So I propose to explain how I have developed the skeleton, measured the skeleton of this supercluster. So I have first of all built a catalog of spectroscopic sources in order to have access to precise position in the cosmic web. So I used 2MRS, SDSS, and other catalog in order to have the most complete catalog of this supercluster. After that, I have modeled the skeleton using Disperse, an algorithm developed at IAP, and in 2D and in 3D. And then for each galaxy, I measured the distance to the closest filament and to the closest cluster. after that, I have extracted cutout around each galaxies of the catalog in order to extract the morphological aspect for each of them. So I've used model fitting in order to have access to the CERSIC index, an indicator of the morphology. And I am using also visual inspection to classify in 4 main classes, ellipticals, lenticular, spiral, and irregular galaxies. And in parallel, I classify also galaxies by local interactions. So I see a lot of mergers, tidal tails, and other features corresponding to the interaction, local interaction. So I have mapped them in the cosmic web, and that you can see here in this map, these results. And what we see is that we have everywhere a large number of interactions. And we see these mirror mergers, which appear close to the spine of the skeleton, which is an expected result due to the position, preferentially position in the cosmic web. I have also measured the morphological segregation in the 2 regions. So what we see is that we have mainly evolved galaxies, so ellipticals and lenticulars galaxies in the region of the cluster region, and close to some groups in the main filament region. And we have a large number of spiral in the main filament region, along the filaments and in a less dense region. I have directly measured this using this plot, so the distance to the cluster versus the distance to the filament. And what we see is this clear gradient in median, showing that we have mostly early type galaxies close to nodes and close to the spine of the filament. And we have more late type galaxies in the filament and around filament close to void. So what we can say with this result is that we have directly 2 evolutionary stages in the 2 regions, with very evolved clusters in the cluster region and more early stages of galaxies in the main filament region. So after that, we have tried to measure some kind of alignment in this cosmic web. So it is a work in progress, but what we see in the shape correlation function is that we have this kind of alignment for galaxies close to nodes, close to cluster. It seems that galaxies, semi-major axes, are aligned toward the cluster direction. So which is an expected result, but never measured for the Pisces-Perseus supercluster. And currently, I'm searching for a spin filament alignment signal. So this is in progress, and I would like to use a bit the rest of this time to talk a bit about the ground space synergy, and especially about the early release observation of Perseus. So the Perseus cluster is one of the main cluster of the superstructure. It is directly linked to the cosmic web with 3 filaments. And during the early release observation, we used the CFHT data to produce the first multi-lambda analysis of the Perseus cluster. And at the end, we obtained the deepest luminosity function for Perseus. So it was really a great result. So thank you, my collaborators, for this fantastic work. And in parallel, I have also used the early release observation to measure some kind of interaction in the outer part of galaxies. And especially, I have worked on the disk break, which corresponds mainly to mergers, minor mergers in outer part of galaxies. And we have used simulation in order to interpret that. So the main message of this two paper is that the cluster can produce tidal effects on the outer region of disk and produce some higher star formation in the outer region of galaxies. So it was a great results and a specific application on this superstructure, and I continue work on this supercluster. So I have two papers in preparation in order to characterize the size and the morphological aspects of the superstructure. And I currently also working on the alignment, as described before. And thanks to a recent proposal at CFHT accepted, I will also use SCG fitting in order to have access to additional information on galaxies such as star formation and stuff like that. And the idea is to produce the radial profile for different colors and find some feature in the outer part of the galaxies, such as disk break, and maybe study this disk break in different environments in this superstructure. So it is in the upcoming work, and I will just say that CFHT is really powerful, and especially it's really key in the work on Euclid. And so I continue also my work on Euclid, and I will also go to CFHT in coming months. So I'm really happy to have met you before, to just have an idea of what kind of works is done at CFHT. So thank you for that, and thank you for your attention.
Very nice. Let's start with Mike Hudson.
Hi, that's very nice. On the issue of alignments, especially with the filaments, some simulations have proposed that the alignment sense actually flips, that the lower mass ones being aligned one way and the higher mass ones being aligned the other way. You didn't put, at least I didn't see, mass as a function, as one of the things to divide the sample by. So I was wondering if that was also part of the plan.
Yeah, I think it's important to consider the mass. So yeah, I don't speak about the mass, but I have tried to have an idea of my population in this supercluster. So we have mainly very massive galaxies. So I cut the dwarf, I think, by the spectroscopic information. And about the alignment, we know that this phenomena can exist, and we will probably try to explore this if we have trends of flip around the outer region of the filament and some stuff like that.
Great stuff. Let's thank the speaker again.